Sports. It's in the game. works. So let me share my presentation. Okay, so I hope you see now the header foil photovoltaics third unit crystalline silicon solar cells. Can you see it? Okay,
Yeah,
and now let me switch to full screen mode. Okay, it looks like that here, for some reason, I can't switch to full screen mode. Do you see it well? I mean, does it fill the whole screen?
It's okay, Professor Bennett.
Oh, okay, then let me switch to the next page and check whether you can follow it.
Okay.
Okay, now you should see the first page.
Exactly.
Okay, fine. Okay, this picture you have seen already, I think, at least twice. It shows just a schematic view of the standard crystalline silicon solar cell as it was the dominating cell for the last 2 decades. And please let me just quickly recall, here we have the p-dope base n-doped emitter, which is roughly half a micrometer thick. The total cell is roughly 180 micrometers thick, a very thin unreflective coating. Here the red dashed one, then the metal fingers which lead to the bus bar on the front side, and the whole area backside contact, which here it's stated with a back surface field. I will explain later what it means. And at the moment, the industry is converting to the passivating emitter and rear cell, the so-called PERC cell, which we see on the next page. This picture you have also seen already. This is now the PERC cell. I mean, the conversion of the whole industry, I would say, is done roughly to 60 or 70%. That means roughly 60 or 70% the volume production of crystalline silicon is already this type of cell. The rest is still the previous one. And the only difference is at the backside of the cell. You see, it's the backside of the cell. The whole area aluminum layer is replaced by another dielectric, which is an aluminum oxide silicon nitride double layer. So it means this blue hatched on the backside is this double layer. That means the double layer is not highlighted here, but it is a double layer. And this dielectric is interrupted at certain points, and this is not by scale. The area of the dielectric, or the area where the dielectric really covers the backside of the cell, is much more than the contact area here of the aluminum back contact. And the reason for this is, as I explained already, the dielectric passivates the backside much better than the aluminium does. The aluminium basically does not passivate at all. Passivation means reduction of recombination centers, which reduce the charge carrier lifetimes. On the front side, you see we have almost the whole front side already covered, also in the previous type of solar cell, with this anti-reflective coating, which is the same time passivation layer. On the front side, it's only silicon nitride. On the back side, silicon nitride alone would not work, and therefore we need this double layer of aluminum oxide and silicon nitride. And of course, it's more effort, but it's worth the effort because the improvement of the performance cell is so much that it's worth to take this additional effort. And in a few years, the whole industry will have converted to that type of solar cell. That means this, what you see here on this picture, is just a schematic of the dominating type of solar cell in crystalline silicon technology at the moment. Okay, the next picture is the band diagram of a crystalline silicon solar cell not illuminated. Usually these band diagrams are given not illuminated because then they are simpler and the most important features are seen. I mean, in the top part of the picture, this is just a cross-section of the cell. You see the p-doped layer and the n-doped layer is not by scale because I said already the total cell is roughly 180 micrometers and the n-doped layer is just half a micrometer roughly. So that means it's basically very near to the surface. And the hatched areas are the metal contacts. On the back side, it's aluminum. On the front side, it's silver. And the lower picture, in the lowest picture, we see the conduction band edge and the valence band edge. And as a dashed line, we see the Fermi levels, the so-called Fermi levels. The Fermi level is just that energy at which the occupation probability of a state is 50%. Roughly, it just separates the occupied from the unoccupied states. I mean, this is clearly visible in the metals. You see the metal, the band is filled up to the dashed line, and above it, it's empty. In the semiconductor, it's a little bit more complicated because here the Fermi level is in the band gap. Therefore, of course, we need to have this view of 50% occupation probability if there would be a state. Okay, here we see the band gap. And what's interesting is, and for those who it's too complicated, say, just ignore what I now say. You see at the metal contacts, the band diagram looks quite complicated. You see here it goes up, and on the other side it goes down. And what we recognize here is basically a Schottky barrier. That means usually a metal to a semiconductor forms a Schottky barrier, which in principle would be a Schottky diode. But of course, we don't want a Schottky diode here. We just want metal contacts, and this is the reason why we dope it very highly. That means directly at the contacts, the semiconductor material is so highly doped that the Schottky barrier becomes very narrow. And that means the charge carrier can tunnel through it. I mean, classically it's forbidden, but quantum mechanically it's possible. If this barrier is very narrow, the charge carrier can tunnel through it, and basically the barrier is not seen for the charge carriers. And that means that the contact appears as if it were ohmic, and such a contact is called a quasi-ohmic contact. That means one should be always aware. I mean, usually in semiconductors, what one calls an ohmic contact, that means just with an ohmic current voltage behavior, in reality is usually a very narrow Schottky barrier. Okay, this is just a side comment for the experts among you. For the others, it's sufficient to say, to notice that we have here a PN junction. A PN junction, as any ordinary diode and ohmic contacts on both sides of these PN junctions. On the back side, you see we have it on the front side as well, but I will focus on the back side here. That means the right side. You see we have here this step in the bend edges. Both bend edges, they are always, parallel to each other because the bend gap, of course, is fixed. And you see, this is called what the back surface field, because with a change here in the bend edges, always an electric field is associated. And you see here, in principle, we have a barrier for the electrons, and something which is supporting collection for the holes. And this is called the so-called back surface field. And this back surface field is generated by aluminium, which is diffusing in from the backside. Aluminium is a group 3 element, and therefore is a dopant as boron is. And that means the aluminium, which is diffusing in from the backside, is enhancing the doping here at the backside and creating this so-called back surface field, which keeps away the electrons from the wrong contact and supports the collection of the holes. And this is a sort of quasi-passivation there. It's not a real chemical passivation, it's a field passivation, an electric field passivation, which is better than nothing, but it's by far not as good as a real chemical passivation by a dielectric would be. And in the case of the PERC cell, here we have this passivation, and this is the reason why the performance of the PERC cell is clearly better than of the standard aluminum back surface field cell. Okay, the next foil you also have already seen. It highlights again the difference between crystalline silicon technology, which is roughly 50% and 95% of the market, and thin film technology, which is only 5% of the market. And in crystalline silicon technology, we purchase wafer from a wafer manufacturer, either a multicrystalline wafer or a monocrystalline wafer. Monocrystalline are usually recognized by these cropped edges, and one should also say the monocrystalline percentage is increasing over the last few years and will continue to increase, because it's certainly not surprising that the better efficiencies are reached by the monocrystalline base wafers. Okay, and then the next step is the cell manufacturing here. About this I will talk today, and then follows the module manufacturing, about which I will talk in 2 weeks from now. And you see, in thin film technology, we have a substrate, usually it's glass, and then we make the cell and the module together. About this process I will talk next week. Okay, here we have an overview of the typical process sequence for manufacturing of a crystalline silicon cell. It starts with wet chemical cleaning and texturing. Okay, here shown, here we have the wafers. It's just p-doped material. They come into a bath of some etchant. It could be either an alkaline or an acidic bath. For monocrystalline material, one would use an alkaline bath. For multicrystalline material, one would use an acidic bath. And what is done, that salt damage is removed, salt damage removal, because before that, of course, all these wafers are thawed from an ingot, and then of course the surface still has the salt damage, because thawing, of course, is a rather how to say, coarse process. And at the same time, we do something which is called texturing. That means it's a micro roughening of the surface. I will explain in a minute what the purpose of this is. The next step is in principle is a core step. It's a phosphorus diffusion from the front side, because this makes a PN junction. Okay, in this case, you see the wafers are keep back by back. The reason is just to protect the backside against phosphorus diffusion, and also to increase the loading. By this back by back loading, we can increase the loading of the furnace by a factor 2. And I should emphasize, I mean, there's also a single wafer loading possible, because the phosphorus at the backside in principle does not disturb. It can even improve the performance of the cell by the so-called gettering process. But this is beyond the scope of this lesson. Therefore, I will just mention it at that point, but will not further embark on it in the further course of this lesson. Okay, in principle, you see we have here a heated tube. It could be either ohmic heating as shown here. It could also be infrared lamp heating. And then we let in a phosphorus containing gas. And this phosphorus containing gas, it deposits a phosphorus containing layer on the wafer, and the phosphorus starts and continues to diffuse in and to make the PN junction. So this dashed line symbolizes the PN junction. That means the initial wafer was p-doped, and that part from the front side, the phosphorus has diffused in, becomes PN-doped then. That means in this process, we have created the PN junction, which is somehow or something like the heart of the crystalline silicon solar cell. The phosphorus glass, which was deposited here, okay, this is this orange layer here, has to be removed in the next step because we don't need it, and it's also hygroscopic. That means it would just disturb. That means it's just a wet chemical etch to remove the phosphorus glass. Okay, the next step is the deposition of the anti-reflective coating, which at the same time is a passivation layer. That means a layer which reduces the recombination centers at the surface. At any semiconductor surface, we find a lot of defects, and a big percentage of these defects acts as recombination centers, just reducing the lifetime and thus the diffusion length of the charge carriers. And therefore, we need this passivation layer, which is usually done in a plasma deposition process. That means we have here a high frequency plasma, and in this high frequency plasma, the chemical radicals are created which trigger this deposition process of this silicon nitride layer here. In the next step, we make the metal contacts by a screen printing process at the front and back side. You see here is symbolized the front side. On the front side, we print these fingers and bus bars. On the back side, for the standard cell, we print just the whole area aluminum layer. And the final step is an annealing of the metal contacts. This is a step which really makes then the contacts. And you see also in this case, also the contacts have to be etched through the anti-reflective coating, because the anti-reflective coating is an insulating dielectric, and therefore, of course, we must get, or the metal of the fingers, or the silver of the fingers must get into contact with the semiconductor material to make this contact. Okay, you see here on the left-hand side, the blue boxes, it's in principle, again, what I just explained. The two orange boxes, this is a modification which has to be made for the new PERC cell, because you might have noticed the process flow which I have described now is just the old aluminum back surface field cell. For the new one, for the PERC cell, we not only need a passivation layer on the front side, we also need a passivation layer on the back side. That means after this deposition of the passivation layer of the front side, you see this is front PCVD silicon nitride, we have to deposit this double layer of aluminum oxide and silicon nitride at the back side. And in the next step, of course, we must interrupt this layer at certain points just to be able to make the back contact. And this is done by a laser ablation process of the rear dielectric. That means at certain positions, we just remove then the deposited double layer of aluminum oxide and silicon nitride again here at the back side, and afterwards we print again, as in the previous step, also on the back side, the aluminum layer. Okay, I promise to explain why we need this wet chemical texturing of the silicon surface. First, I want to show you two SEM pictures, scanning electron microscopy pictures. You see, that would be the alkaline edge. If you use an alkaline etchant, we get these micropyramids on an 100 surface. But here I should mention for photovoltaics, if one has monocrystalline silicon, it's always a 100 surface, and this surface is also the by far widest used in microelectronics. That means this is basically the standard surface which is used for device manufacturing in both photovoltaics and microelectronics. And the side faces of these pyramids, they are 111 surfaces. And you see these micropyramids are created just by the fact that an etchant is chosen, which etches the 111 surface roughly by 2 orders of magnitude slower than the 100 surface. And therefore, of course, at the end, only 111 surfaces remain. And these 111 surfaces, they form these faces of the pyramid. This, of course, does not work with multicrystalline silicon, because the prerequisite for that is that we have a 100 surface. In multicrystalline material, we have just a random distribution of surfaces of every neighboring crystal grain has a different surface. And therefore, here we use an acidic edge. And in the acidic edge, we get just this random structure here. The purpose of this structure is always the same, and this is shown in the lower picture. You see it's here, it symbolizes here the structures at pyramids, but of course it would be the analogous element also for the random structuring or random texturing of the multicrystalline material. You see, if a light beam comes here, if the surface would be smooth, a certain percentage of this light beam would be reflected. And here you see the reflection would go into this direction, and a part of this reflection still can enter the silicon. That means, you see, by this texturing, we increase the probability that a photon, which might be reflected for the smooth surface, still has the possibility to enter the silicon. And the second is also shown. You see the path length through the silicon in average is increased. That means this texturing has two purposes. First, increase the incident radiation, that means reduce the reflected radiation. And secondly, extends the path length through the crystal. And of course, extending the path length means increasing the probability that finally a photon is absorbed. That means just by texturing the surface, the reflection, which is roughly 35% for a smooth surface, is reduced to about 10% on the textured surface. And this is really quite a big difference. You see, this is a big difference in performance for such a simple measure. And the second one, you see, since the path length is increased, in principle, thinner wafers become possible. That means, and of course, thinner wafers mean we save money because we don't have to purchase so much silicon material. Okay, this is just an example how such a machine looks like. Okay, in this case from Centrotherm, which is a German company. You see this is such a wet bench. Here several baths are in sequence, and here on this small picture you see just how the wafers, they are running on these Teflon rollers and moving through this bath. Okay, here at the end they are just entering the bath, and here's also topside rollers which press them down under the liquid surface such that they are etched from all sides. And there is also, I should say, not mainstream process. I would like to mention it because this is one of the fields of active research at our university. An alternative to make this texturing instead of the wet chemical process would be a plasma etch process. And it's done with such a machine as we have it also in our laboratory here. In principle, it's a high vacuum chamber where we have here a capacitive coupling from a high frequency generator. We use 13.56 megahertz. And here we have an inductive coupling through a coil of the same frequency. Here we have the gas inlets, I mean, sulfur hexafluoride and oxygen. These are standard gases, but there can also be other gases used. The essential gas is, or the essential constituent or atom which we need is fluorine, because fluorine is that one which really etches the silicon. And then we burn the plasma here, and just by the so-called self-bias of this high-frequency field, there is always to the high-frequency field a superimposed DC field created. And the DC field is such that the plasma itself is positive relative to the wafer. That means all the time we have a bombardment of the wafer surface by positively charged ions. I mean, the minuses here are just the electrons in the plasma. And by this bombardment in combination with the chemical edge attack by the fluorine, structures like this can be created. You see here very high aspect ratio structures. Macroscopically, such a wafer is really black, and therefore such a surface is called black silicon. And the lower one is with more moderate aspect ratios. But both of these has the advantage over the wet chemical edge that firstly we achieve much higher reflection reduction, and secondly any kind of surface can be textured by this plasma etch process, whereas the wet chemical process, it needs already some pre-roughening for edge attack, whereas the plasma etch, it also works for absolutely smooth surfaces. And the wafers of the future, which might have been produced by curveless processes, which are currently under development, that means which will replace the sawing processes. These curveless processes give usually very smooth wafers, which cannot be structured wet chemically. So that means this research on plasma etch in principle is for a future perspective when the standard mechanically sawed wafers will be replaced by so-called curveless separated wafers. Okay, here it's shown actually how much the reflection reduction is. And I mean, I will concentrate here on the dashed lines. The full lines, they are the absorption. I will concentrate on the dashed lines, which are the reflectivity. In this case, you see wavelengths resolved. You see that would be the upper dashed curve would be just the reflectivity of a smooth wafer surface. The second black curve here would be the reflectivity which can be reached by an alkaline texturing. And you see the red dashed curve, that is what we can reach by plasma etching with the moderate aspect ratio, and the blue dash curve is that what we can reach by plasma etching with the very high aspect ratios. Okay, that means this reflectivity reduction, this of course is the motivation of this kind of research. Okay, let's now come to what I call the hard process, or which makes really the heart or the core process of the solar cell manufacturing, which is the creation of the PN junction. This is done by such a quartz tube, which is heated up to 800 to 1000 degrees centigrade. The wafers are in a quartz boat. As I mentioned it already, they can be either back by back, or they can also be in a single arrangement. And then we use three gases. One is oxygen, one is a carrier gas, which usually is nitrogen, but also could be argon. It's a gas which really does not participate in the reaction. And the last one, it's not a gas, it's a liquid. It's phosphorus oxychloride. And this phosphorus oxychloride, also called POCL, is, since it's a liquid, it's fed to this quartz tube by a so-called bubbler. That means it's basically just a carrier gas going through the liquid, and the bubbles taking with them always a certain amount of this phosphorus oxychloride, which has a boiling point roughly above 100 degrees centigrade. And to have a stable amount of these molecules always taken with the bubbler gas, this liquid must be very well temperature controlled in this bubbler vessel. And then these gases come into here and thermally triggered. I remind you, the temperature is quite high. This chemical reaction is triggered. That means the silicon reacts with the phosphorus oxychloride and the oxygen to a substance which is called phosphorus glass. You see, it's basically a glass. A glass is mainly silicon dioxide combined with phosphorus oxide, and chlorine is released here in this process. And then in the next step, you see when this phosphorus glass is grown, since we have here quite high temperature, a substantial amount of the phosphorus will diffuse from this phosphorus glass into the silicon wafer, and then making the n-doped top layer and the p-n junction. Here are some photographs of such a diffusion furnace. We see here in this picture, we have just a robot, and it's about to move the wafers towards a cantilever, which is used for loading it into the heated furnace tubes. You see this red color is from the big heat of these furnace tubes, in which finally the wafers have to be moved. And typically in such a furnace, we have several of these tubes above each other, typically 5 or 6 of these tubes. And on the top right picture, we see how the cantilever moves the wafers into the quartz tube. In the lower one, it's a removal, not the same one, it's another one, the removal of the still hot wafers from a small lab furnace. Okay, the next picture is again the wafers on the robot arm. And the last one, sorry, the last one here, bottom right, is here's a cantilever without wafers, here with a pedal on the cantilever, which is ready for accepting wafers from a robot arm like this, because it's clear the loading and unloading of these systems is done fully automatically by some robots. There's a second possibility to do this diffusion, And don't worry if you see some German text here. I mean, I translated everything. That means just ignore the German, read the English. So this is about N-doping by thermal diffusion in a so-called inline furnace. You see here's the difference. Instead of having several wafers in a boat, now we have a conveyor line or a conveyor belt where in a continuous movement, the wafers move through this heated furnace. Here we have an inert gas curtain just to separate the inner side of the furnace from the outside. And you see here we bring through a nozzle, as we have a spray nozzle, which brings the phosphorus to the wafer surface, and usually phosphoric acid is used, but as an alternative, okay, we could also use a phosphorus-containing paste. Then, of course, we would not use a nozzle. Then we would use a squeegee or something to deposit it on the wafer surface. And then it goes here through this heated furnace, and the phosphorus diffuses again into the wafers. The advantage of this process is that it's an inline, that means a continuous process. That means every wafer sees precisely the same process, whereas in the previous process, of course, that we might have a certain position dependence in the boat or something else. A disadvantage is, you see, whereas the previous one is a fully sealed furnace. Here we have just a separation from the outside by this inert gas curtain, and therefore, of course, the contaminants in this process are higher than in the previous process. Basically, this is a cheaper process for non-leading edge technology, whereas the previous one was a more expensive process for leading edge technology. Okay, let's now just recall the proportions of the cell. You see, I have drawn here the surface of such a textured cell. The total cell thickness, okay, the whole cell would be this one. It's roughly 180 micrometers thick. This textured region is 5 to 10 micrometers. That means this height of these pyramids here in this case are 5 to 10 micrometers. And then you see the PN junction, which is a dashed green line. It precisely follows this texturing. So that means this is a PN junction. And then we deposit an additional unreflective coating, which is typically 70 nanometers. The reason is it must fulfill a so-called lambda quarter condition to be very effective. That means the thickness must be the wavelength of which the reflection we want to reduce a quarter of this wavelength in this material. And this is then roughly 70 nanometers. And I said again, this is roughly a factor 1,000 thinner than a human hair. And you see also this anti-reflective coating here in blue. It follows precisely this textured surface. So this always should one keep in mind, because usually in the schematic drawings of the cells, this texturing is omitted, and therefore one just sees a smooth surface. But in reality, one always should be aware that one has this texturing, and both the PN junction here in dashed green and the anti-reflective coating both just follow the surface of this texturing. Or the surface topography of this texturing. And the purpose of the anti-reflective coating is, of course, to reduce the reflection even more, and this is shown on these pictures. Again, we see the reflectivity in dependence on the wavelength, and in the left picture we see, okay, the red one would be as the wafer comes after thawing. That means you see then we have said thaw damage removal, then the reflectivity has even increased, but after texturing, this is a blue curve, it has been reduced. Okay, this is a texturing alone. On the right-hand side, we see how the texturing with the anti-reflective coating together performs. That's for, I mean, the black is just the unreflective coating. Okay, I can also explain it. So the black one, it's the same as here on the right-hand side, or the similar one, just without any treatment. And then with unreflective coating, we would get the black curve. Okay, this point would be precisely the point where the lambda quarter condition is fulfilled. That means where the lambda quarter condition is fulfilled, we really have reflectivity 0, but this of course is only possible for one single wavelength, in this case roughly 600 nanometers. If you have the texturing, we have the red curves. You see, the red curve would be the texturing alone, and the orange curve would be the texturing plus the anti-reflective coating. And you see this, of course, is the best performance. That means texturing and anti-reflective coating together get or achieve the lowest reflectivity. That means the best usage of photons. That means, and it's really, I mean, if you compare it with the black curve, it's really a very, very big improvement. As I said already, usually the reflective radiation would be more than 30%. With both together, it goes down to 3 to 4%. That means this is really, in principle, two rather simple measures which improve the performance of such a solar cell very much. Okay, the next one would be the plasma-enhanced chemical vapor deposition, by which the anti-reflective coating is deposited. And in principle, it's a similar equipment which I've shown for plasma etching. The only difference is that it's operated in a different mode. It's operated in a deposition mode, and of course different gases are used. The gases, I mean the process I will want to concentrate is here on the top right, red framed, where you use the gases silane and ammonia. And in this plasma, a reaction is triggered which leads to the deposition of an amorphous silicon nitride layer, which also contains some amount of hydrogen, which is also important, and hydrogen is finally received. And this amorphous hydrogenated silicon nitride layer, this is firstly the antireflective layer, and secondly, it's the passivating layer. And this is a so-called plasma-enhanced chemical vapor deposition. This is used here for this arc layer, but it will also be used for a cell which is called the HIT cell. I will explain later what it is. And it's also used in thin film solar cells, as we will learn next week, for example, for the deposition of amorphous or microcrystalline silicon, which would be referred to these processes to which I will come next week. Okay, here we have an animation of another kind of deposition, of plasma-enhanced chemical vapor deposition. In this case, you see in the previous picture, the plasma was just created by a capacitive coupling of a high-frequency field. Here, the plasma is created by a coupling of microwaves. You see all these tubes, they are microwave tubes. That means here and on both sides of these microwave tubes, there sits a microwave generator and feeds the microwaves into these tubes. And these tubes, they create a plasma in the gas around this tube. The gas here again is silane and ammonia. And the same chemical reaction, which was described in my previous picture, is triggered here. And what we see here, you see here many wafers, in this case, multicrystalline wafers, as you can see here, in some sort of wafer array arranged. And these wafers, they move continuously over these plasma generating tubes. And this machine, I mean, it was built by Roth and Rau. Now, meanwhile, it's called Meyer Burger Germany, which is still a leading equipment manufacturer, especially for this kind of process. I said already on the back side, we have this double layer. You have this double layer of aluminum oxide and silicon nitride. And the aluminum oxide layer, it's usually deposited by another process, which is called atomic layer deposition. An atomic layer deposition works in a sequence that we have alternating pulses and purges. First, we have a pulse of a gas, which is trimethyl aluminium. You see one aluminum atom with 3 methyl groups. That means the methyl group here is always one green sphere. And these adhere to the surface here, okay, as seen here. And everything what is not adhering to the surface is purged away. Then in the next step, we let in water vapor. And the water vapor, it brings the oxygen. The oxygen reacts with the aluminum. The hydrogen is finally removed, and then it starts again from this side. Okay, the lower picture is just from another source. It explains the same. That means, you see, this is why this process is called atomic layer deposition, because one has these alternating precursors, and just by this pulse and purge cycle, one can in principle count the atomic layers. That means by this process, you can just deposit a certain predefined number of atomic layers. Okay, in the last picture, you see you have it in chemical formulae. You see, okay, this would be okay. Initially, it's assumed that we have this oxygen layer. Okay, it's usually terminated by hydrogen. Then we get this trimethyl aluminium. The aluminium bonds to the oxygen. And then finally, we still have some remaining methyl groups, but these will be replaced when the oxygen in the water comes in, because then the aluminum will be oxidized, and then again we have the terminated bonds by this oxygen and hydrogen groups or hydroxide groups, and then it starts again from the left-hand side. You see, this is quite a clever process technology. It was invented by a Finnish scientist not so long ago. I mean, roughly 30 years, I remember quite well. I myself was a PhD student when this technology, this atomic layer deposition technology, was invented. Originally, of course, just for scientific purposes, but as you can see here, meanwhile, it runs in production in photovoltaics, and of course, it also runs in production in microelectronic manufacturing. Okay, then I said already, the contacts, they are made by screen printing. That means both front and back contacts are made by screen printing. Screen printing is a very simple technique. I mean, for example, you can have some pictures on your T-shirts screen printed. In principle, it's just a solar cell. Here we have the screen. We have a paste, which is moved by a squeegee across this wafer. Okay, the squeegee also presses it down and presses this paste through the open regions of the screen, and then something like this remains. And since the paste, of course, has a certain viscosity, after some time, of course, you wouldn't see the structure any longer. You just get something which has flown apart. That means a shape, as I described at the moment with my cursor. So that means screen printing. This is a rather simple process. Of course, I mean, in this case, when we use it for solar sets, it's a little bit more elaborate in comparison to that when you screen print a T-shirt. Okay, after this screen printing process, we need to bring the wafers again to a conveyor furnace for the so-called firing process. And in principle, you see this is here's a conveyor belt. Here are the wafers on the conveyor belt. Here I have chosen an example with infrared radiation heating, but of course it could also be ohmic heating. Again, we have here a curtain, or okay, here in this case we can even use air as a curtain to separate just the inner of this furnace from the outside. And then we have different heating stages. You see, it's indicated by the density of the infrared lamps. It becomes hotter and hotter from the left to the right. In the first step, between 200 and 300 degrees centigrade, we are just drying the printing step, and it's in fact it's 3 printing steps. Of course, it's clear it's 2 for the front side, for the back side, but on the back side we have, in addition, to print some solder pads because aluminum cannot be soldered. Therefore, in total, it's 3 printing steps. That means in the first step, and of course these first 2, they are done for every printing step. Only the third one is done only at the end. So that means the first is just the drying step. You just evaporate the solvent in the paste. The next one, it runs between 400 and 500 degrees centigrade. It burns the binding agents. There are binding agents in the paste, and they go, of course, to the exhaust. And the last one, which is the most important one, it runs up to 800 degrees centigrade. It's firstly the etching of the fingers through the anti-reflective coating. I said already, one has to etch through it because this is an insulating dielectric. And at the same time, in the paste, of course, the metal is in forms of flakes or balls. That means these flakes or balls are sintered together in this step. And at the back side, in addition, silicon aluminum eutectic is formed. And this eutectic finally makes the right contact on the back side. And at the same time, it makes this additional aluminum doping, what I mentioned, to create the so-called back surface field by the additional aluminum doping. And then the last step is it cools down, and the typical transport velocity, okay, it was somehow lost, this amount, but no, here it's given 1 to 5 meters per minute, and such a conveyor belt is up to 10 meters long. That means it's also quite a big equipment, and this is the second most critical process after the PN junction formation. Okay, then is a last process which was not mentioned on my initial foil, but which is also very important. It's the so-called edge isolation process, and it's shown by this schematic. You see, in principle, we have now the p-doped region, we have the n-doped emitter, and the n-doping, of course, is also at the edges because we did not protect the edges. And here we have the back contact, and you see, in principle, we would have now a shunt along the edges from the front side to the back side. And therefore, we have to interrupt this shunt, and this can be done either by a laser cut. If you just make a laser cut of a trench, which is deeper than the PN junction, and then it separates here this was, or it interrupts this shunt. The second possibility would be that we just use again a wet chemical bath process, and we would use this then after PSG removal. If you remember, after the doping, we had this PSG removal. We could have a second wet chemical process with the wafer just half submerged and just removing the doping in one half of the wafer. And this, of course, again would interrupt here this shunt to the backside. If we wouldn't do this process, this solar cell would have a very bad fill factor and a very poor performance. Okay, the last 5 minutes I will use to introduce the 2 leading edge solar cell concepts, which deviate a little bit from the mainstream concept, but these two concepts give the best efficiencies. So this is a sort of Mercedes or Rolls-Royce of the solar cells, but of course these cells are also more expensive than the other ones and even more expensive per watt peak. One is the so-called HIT cell. HIT stands for heterojunction with intrinsic thin layer, which was originally invented by Sanyo, but has meanwhile seen a certain revival, and especially by Meyer Burger, which is not, it's just 30 kilometers from here in Köthen or near Köthen, just ramping a new gigawatt line. It's a Swiss company, or it's originally a Swiss company, but meanwhile also with a big basically, what I said or as mentioned already in the previous point, they've purchased the German company Roth and Rau, and now they are starting to make their own solar cells. The original patent is already from 1991. That means it's meanwhile run out. But of course, there are several additional patents. And modules are in the market by Sanyo and later Panasonic. Sanyo was taken, I think, 10 years ago, was overtaken 10 years ago by Panasonic. Both are Japanese companies. And meanwhile, we see here efficiency of more than 21% in module production. And if you look at the schematic of this cell, you see it's very simple. It's an N-dope base. This, of course, is the main difference. For the other cell concept, we had a P-dope base. It's also textured, which is not shown here. And then we have on both sides an intrinsic amorphous silicon layer. Intrinsic means undoped. And here a P-doped on this side and an N-doped on this side. That means one is here to make the PN junction and the other makes a back surface field. And then we have something which is called TCO, transparent conducting oxide, and the electrodes. In this case, we show a bifacial cell. Bifacial cell is one which can be illuminated from both sides, which is also an increasing market segment. But of course, this cell is also available as a monofacial variant. And the interesting thing here is, you see, you don't have to make a PN junction by a high temperature process, and you also don't have this final firing process for making the metal contacts. That means you see this HIT process, or as now it's mostly HIT is a name by Sanyo. Meanwhile, it's mostly, in most cases, called just heterojunction silicon cell. You see, this is easier to manufacture than the classical standard mainstream process, but gives higher efficiencies. So it's very interesting, at least if you do it in the right way. And the second one of these processes is the interdigitated back contact cell. The interdigitated back contact cell, I mean, I mentioned it already. You see the first solar cell, if you remember 2 weeks ago, in principle, it was a back contact cell, also of an N-dope base. I mean, this is a paper of these 3 people who invented this first cell. And since mid-1980s, there are high-performance cell on the market by SunPower. This is a spin-off of Stanford University. This guy, Professor Svensson, founded this company already in the 80s and then sold it to, or most of it he sold to Total, an old company, a French oil company. And this cell, I mean, it's the same principle as what is shown here as a cell from the solar, from this International Solar Cell Company from Constance. You see, both all contacts are on the back side. We have an N-type silicon, and on the back side, partially we have a PN junction, and partially we have just this much more N-doped junction here, and the one goes to the one kind. Here's a plus contact and here's a minus contact. Here's a yellow one. It's an dielectric which insulates the two from each other. This is of course important in this type of cell. One has to separate plus and minus pole, and on the front side we have something which is called here a front surface field. That means it just has the task to keep away the charge carriers from the surface, where we have the surface recombination centers which could reduce the charge carrier lifetimes too much. And these two cells, I mean, they are only a niche market, I should emphasize, but they are the best performing cells which are in the market at the moment. And the interesting thing is the time where they were invented for both types of cells, I mean, it's almost more than 2 decades ago. Okay, with this type of cell, I will finish here, and I would allow, let's say, 3 questions, because then I have to go again to my own lessons here. Okay, are there any questions? Okay, this time I also checked where I find the chat. Maybe I see something in the chat. Okay, but I don't see a question. Okay, does somebody have a question? She or he just might ask it now.
Thank you, Professor Bernard, for the excellent lectures. It was very, very details, and maybe I do not know when anybody questions. Otherwise, I have questions. You have shown some experience at your lab, and I know also your university had a good cooperation with the Fraunhofer Institute Halle. Can a student learn to construct a cell, solar cell, in your lab as well as in the Fraunhofer Institute during his study, or they learn the basic?
Was that a comment or a question?
A question, yeah.
Can you repeat? What was the question?
What is the scope of a student to produce a cell, a solar cell, in your lab as well as in the Fraunhofer?
Okay, first I should like to emphasize ourselves, we don't produce cells, because you see, to make a cell, I mean, of course you can make a cell easily with a poor efficiency, but to make a cell with a competitive efficiency, you need a lot of equipment, and we even couldn't pay just to operate this equipment. And just to give you an idea of a figure, to purchase, I would say, to purchase all the equipment for a whole manufacturing line, to make good equipment, would be at least, I would say, 20 million euros or $20 million, and to operate it would be, say, $200,000 per year. So it does not make sense for a university institute, and also does not make sense for the Fraunhofer Institute to make cells by themselves. That means there's one exemption. I mean, there are some few institutes worldwide, research institutes, not universities, which can make cells. One is the Fraunhofer Institute in Freiburg in Germany. They really have their own manufacturing line, a sort of pilot line, of course, where they do really research in making their own cells. But this is beyond our own scope. That means what we do, we get some wafers from a cooperation partner, make this texturing there, and then bring it back to the cooperation partner, and the cooperation partner finishes the processing of this cell. Because, I mean, it does not make sense. I mean, you must focus, you see, on a certain small part of your research, and especially we as a University of Applied Sciences, we cannot compete, for example, with the big research institutes. We have to look for some niche questions, and one of these niche questions is, for example, the plasma texturing. Another of these niche questions would be wafer halving by thermal laser separation. This would be our second main topic of research. That means our strategy in our own research is to cover some niche questions which is not done by somebody else, where we also can compete with others, or we can compete, or we can, we can publish papers which are competitive, although we have only limited access to expensive equipment. And for the Fraunhofer, I should say, of course, for the Fraunhofer, the situation is much better, but at least at Halle, they also don't make cells by themselves. But what I have presented here, this is really the research which is done here at Köthen. This has nothing to do with the Fraunhofer research.
Yeah.
The Fraunhofer, of course, has much more possibilities, and our students, of course, I mean, you see our students, of course, they can do their master thesis also at Fraunhofer, and I would say roughly 40% of the students do it at Fraunhofer. Another 50% do it with somewhere in the industry, and roughly 10% of our students do their research in our own research project at our university when doing their master thesis.
Yeah. Thank you.
Okay, I will allow one further question because this was a rather long answer. Now I have time for another question if there is one.
Professor Bernhard. Hallo?
Yes, I hear.
Ja, können Sie bitte
hear you.
mal, ja, können Sie bitte mal Nummer 16 oder 15 wenden? Also glaube 15 oder 16.
Yes, but please ask your question in English such that everybody can understand it. Okay.
Okay. It's atomic. It's called atomic layer
Yes.
deposition. I think 15.
Deposition.
16,
Yes. Okay.
or 17.
Yes. Okay.
Maybe.
Yes. Here we are.
Yeah, this one. Yeah, this one. Okay. My question is that it's written. It's repeated in times. Yeah.
Yes. Okay.
How many times exactly? Is there any...
It depends how many atomic layers you want to deposit. If you want to deposit 10 layers, you have to repeat it n times. If you want to deposit 15 layers, you have to repeat it 15 times. And this would be the typical sequences. I mean, since every of these layer, of course, it lasts, let's say, 5 to 10 seconds, and of course, time is money. Therefore, of course, you would only use this process if you want to deposit just a few layers. That means the number of layers is typically 10 to 20. More you don't deposit, and if you wanted to deposit more, you would use another technology. That means ALD is just suited if you just want to have a very precise control of how many layers you want to deposit, and if you don't need a big growth rate, if you just want to deposit a few layers. Okay?
Okay, thank you.
Yes, you're welcome. Okay, then thank you very much for your time. We will see you again next week with the next chapter, which is about thin film solar cells. So thank you very much for your attention. See you again next
Thank you.
week. Bye.
Bye-bye.
Thank you. Bye-bye.